Okay, so starting 10.4, I'm throwing out one problem. It was originally 1 to 13. I'm going to make it 1 to 11. Okay, 31 star means I'm changing problem 31. So the original 31 is not going to be it. I'm modifying it, so I'll show it to you when we get to it. Okay. So I'll plan to do 10.4, go as far as I can, maybe sneak in some of 10.5 today, and then I'll give you a quiz on the polar graphs later. Okay, and see schedule-wise, we are here. So we were supposed to get up to just 10.3. I'm done with 10.3, so I'm a little bit ahead. Okay, and I crossed this out. This doesn't make any sense. But again, it's in my best interest, since I fouled up the schedule, to move everything up, because I don't want to have to give you the last regular exam on Tuesday the 15th before the final exam. So it'd be nice to push it over here. Then I can have at least one day, and you can have one day for questions and answers before our final exam on December 17th. Okay. All right, so let's try to do as much as we can for 10.4. All right, so here's the assignment. And again, I realize sometimes the questions match, sometimes they don't. I have checked at least 31 star. My 31 star, it doesn't matter because it's not going to match the book anyway. I think my 30 matches. So as I do the problems, you'll see some of them match, some of them don't match, but the main thing is that you're learning how to do this stuff, right? So here we go. So the major idea in 10.4 is area. Areas in polar graphs. So here's our formula. Integral from a to b of 1/2 r squared d theta. Okay, theta is going from a to b. Okay, so unlike rectangular coordinates, where x is normally going from something to something, okay, theta is going from, let's say, a to b. So you're sweeping out area in this fashion. Okay, you're moving the angle. So this is a delta theta change in angle as we go along. Okay, and again, you can put this on your cheat sheet. Area is integral of 1/2 r squared d theta, integral from a to b. Okay, so we'll just get our feet wet and try some of these. Again, some of them match, some of them don't match, but we'll see how it goes. Okay. All right, so problem 1. Again, it's my one. I think this one matches, but again, it shouldn't matter. Remember, this is a polar graph. See, what does it look like? I don't know. Right now, we don't really care what it looks like. You can make a table, right? Just like any of the others, but we don't feel like it. So we'll just go to it. Formula is 1/2 r squared d theta. Okay, these are two angles. Okay, so whatever this graph looks like, you're going from what, 90 degrees to 180 degrees. So it has some graph you're sweeping out like this from 90 to 180 degrees, and you're getting some area. So what is the area that we're coming up with? Okay. So 1/2 r squared e to the negative theta over 4 squared d theta. Almost always you take the half out. Okay, 2 times that would be negative theta over 2, or negative 1/2 theta. Okay, so we integrate. And for integration, I do the opposite of differentiation. If I were to differentiate this function by the chain rule, I would multiply by negative 1/2. Since I'm integrating, I divide by negative 1/2 or multiply by negative 2. E to the negative 1/2 theta from pi over 2 to pi. Okay, and notice these cancel out, so I have a negative. Okay, plug in pi. That gives me e to the negative pi over 2. Plug in pi over 2, you'd have negative pi over 4. Okay, so this is sort of the answer, except I don't like to have that many negatives. If you have negative parentheses, I like to just turn them around. Right, remember, the opposite of a minus b is b minus a. So I'll get rid of the negative and just turn these two around. Remember that trick? So the best final answer is e to the negative pi over 4 minus e to the negative pi over 2. Okay, so I'll leave it like that. So little sidebar here. The opposite of a minus b is b minus a. I'm using that trick. Right, negative A minus a minus B, that's plus B, or you can write it as B minus A. So that's all I'm doing over here. Okay, number 5, again, that's my 5. I don't think that matches this time, but at least you learn how to do it. And you're going from 0 to 2 pi. Okay. In case you're wondering, this also is a spiral. If you were to graph it, I mean, you can just plot points, you'll see that it's a spiral, but we don't really care. Okay, so from 0 to 2 pi, simply 1/2 r squared, theta squared, d theta. Okay, take out the half. Radical theta squared is just theta. So I'm integrating theta, d theta. Very nice. So 1/2 theta squared over 2. From 0 to 2 pi, that's 1/4. Plug in 2 pi. 2 pi squared is 4 pi squared. Minus plug in 0, you get 0. So the answer is pi squared. So that's the area. That's the area swept out by this spiral. Okay, and what's interesting is you can have a weird spiral shape, and yet you can still find its area by this technique. And you wouldn't really know how to do it if we were doing it in rectangular coordinates, right? But you can see it is possible by doing this technique here. Okay. And then the next one I'm going to show you was 9. Okay, it says sketch the curve and find the area that it encloses. Okay, and that actually is a question here. So I will have to use up one more of my polar graph paper. Sketch the curve, find the area that it encloses. Okay. So it's r equals 2 sine theta. So let me come up with my graph of r equals 2 sine theta. So I have to take a big time out and work this out. So it's 10.4. It's not the right page anymore, but page 673, I think. But it is the same question. All right, so graph r equals 2 sine theta. The maximum r is 2. So we've done that before. For r is 2, we go to 10 circles and waste the 11th, 12th, 13th, and 14th. Okay. And by the way, when I give you your polar graph, you do the same analysis. You have to have this very same graph paper that has 14 circles. So you divide it, exactly the way that we've done in class. There's no coefficient in front of theta, so I just do my quote-unquote usual angles every 45 degrees. And so r equals 1 is the 5th circle, and one individual circle is 0.2. Okay, so 1, 2, 3, 4, 5 circles, that's 1. I darkened the 1 to make it easier. And 1, 2, 3, 4, 5 for 2, and I darkened that one also. All right, and then this one is just a regular theta. There's no 2 theta, 3 theta, 4 theta, or anything like that. So I just do my every 45 degrees. Pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. Okay. All right, so r versus theta. Okay, we're not supposed to see this yet, but r equals 2 sine theta. Plug in 0. Sine of 0 is 0. So that's a 0. And at 2 pi, it's also 0. So there's 0. And then I divide and conquer, go in half. Cut it in half, you get pi. Sine of pi is also 0. So that's 0. Cut those in half. Pi over 2, 3 pi over 2. Okay. Sine of pi over 2, sine of 90 degrees is 1. 1 times 2 is 2. Sine of 3 pi over 2 is negative 1. Negative 1 times 2 is negative 2. Okay, and keep cutting in half. That one, that one, that one, and that one all have something to do with radical 2 over 2. Now, radical 2 over 2 is about 0.7. Multiplied by 2, 1.4. So I'm either going to have positive 1.4 or negative 1.4. Okay. Now, you can go off the function, or again, just reason it out. 0, 2. So most reasonable would be 1.4. Same thing here. You go from 2 to 0. It wouldn't make sense to have negative 1.4, right? So 1.4. 0 to negative 2, negative 1.4. Negative 2 to 0, negative 1.4. Okay, so here we go. All right, so 0, 0 starts at the pole. However, for 45 degrees, 1.4. Okay, this is 1, and each circle is 0.2, so 1.4 go to the 7th circle. Pi over 2, 90 degrees, r is 2. 3 pi over 4, back to 1.4, so 1.2.4. And then pi, I come back into the pole. So where's the rest of the graph? It just doubles back on itself. 5 pi over 4, negative 1.4. So here's 5 pi over 4, right? But because it's negative, I go back 1.4, which is 7 circles back. Oh, I already got it. There it is. Same for all the rest. 3 pi over 2, so I'm supposed to aim down, but it's negative 2, so I walk backwards 2, so I already have that point. 7 pi over 4, so I'm aiming this way, negative 1.4, so I walk back 7 circles, and again, I already have that point, and then I come back into the pole. So by going from 0 to 2 pi, I trace the circle twice. And yes, this indeed is a circle. All right, so now I'm ready to find the area. Okay, so should I integrate from 0 to 2 pi? The answer is no. I got the entire circle just by going from 0 to pi, and then a double back on itself. Okay, so if you would integrate from 0 to 2 pi, you get twice as much area because you would sweep around 2 times. So now that I'm done with the graph, and again, if I'm going too fast, this is all recorded. You can check the video later. Okay, and all that. So notice I'm only going from 0 to pi of 1/2 r squared d theta. Okay, take out the half. I have 2 squared, which is 4. 1/2 times 4 is 2. Okay, half comes out, 4 comes out. I have sine squared theta. Okay, sine squared, there's an identity. You can put that on your cheat sheet if you wish. 1 minus cosine 2 theta over 2. Very conveniently, these cancel out. So I'm integrating 1 minus cosine 2 theta. So that's theta minus integral of negative cosine 2 theta is negative sine 2 theta times a half. Okay, again, chain rule in reverse. If you were differentiating, you would multiply by 2. Since I'm integrating, I divide by 2 from 0 to pi. All right, so plug in pi. I get pi minus sine of 2 pi is 0 minus 0 minus 0. So my answer is just pi. Okay, the answer is pi. I'm done, but I'll dig deeper. This is a circle. What is the radius? Okay, it's actually not 2. The distance from here to here is 2, but that's a diameter, which means the radius is 1. What's the formula for the area of a circle? Pi r squared. So pi times 1 squared pi. So it matches. Okay, and notice we only went from 0 to pi because by drawing this, you notice that I got the entire circle just from 0 to pi. And if I kept going, I would just double back on itself. So you would have gotten the wrong answer. You would have gotten more than the area because you get the whole circle just after pi. And you see we got the right answer. Okay. Okay, 17. Find the area enclosed by one loop, r equals 4 cosine 3 theta. So I don't have to draw the entire graph, so I'm not going to use up one of these valuable piece of paper. I just need to come up with one loop somehow of 4 cosine 3 theta. So I didn't bother with a very accurate graph. I just needed something quick and dirty. So I made my little chart here. 4 cosine 3 theta. The maximum R is 4. So see, I just real crudely went 1, 2, 3, 4. Okay, so to get a loop, I need to come back into the pole a couple times. Okay, so I started off with R versus theta. How about I plug in 0? So if I plug in 0, I'm taking the cosine of 0, which is 1. 1 times 4 is 4. Okay, now, I could originally think in terms of plugging in stuff like pi over 12. Why pi over 12? Well, pi over 12, plug in here, that would give me pi over 4. So that's ordinarily what I would do if I had to graph the whole thing. But I don't really want to. I just want something quick and dirty. I need something to come into the pole. Okay, now, I know the cosine of pi over 2 is 0. Okay, basically, this is a wasted information, but I wanted to show you what happens if I took the usual numbers of taking pi over 4 and taking 1/3 of that, pi over 12. Okay, I know cosine of pi over 2 is 0. So how can I force this expression to be pi over 2? Plug in pi over 6. Okay, so at pi over 6, plug in pi over 6, I'm taking the cosine of pi over 2, which is 0. Okay, and since I know the cosine is an even function, okay, when I plug in negative pi over 6, I also get 0. If you plug in negative pi over 6, I'm taking the cosine of negative pi over 2, and I know that's also 0. Okay, so I have one branch, one leaf, if I go from negative pi over 6 to pi over 6. So I drew here negative pi over 6, pi over 6, and one loop is like this. And now all they ask for is just one loop. Okay, so I didn't do it very accurately. There's more loops. There's more here and here. There's other stuff. But I didn't bother using one of these guys because I just needed one loop. So I figured out one loop from negative pi over 6 to pi over 6. Okay. All right, so there we go. So integral from negative pi over 6 to pi over 6, 1/2 r squared d theta. Now, you can also tell there's symmetry here, right? So because of the symmetry, I don't want to plug in negative pi over 6 to pi over 6. I would much rather plug in 0. I like plugging in 0. So take the integral from 0 to pi over 6 and multiply by 2. Very conveniently, that 2 will cancel the half, so it's gone. 4 cosine of 3 theta squared. Okay, 4 squared is 16. And then I have cosine squared 3 theta. So I use the identity for cosine squared. Okay, cosine squared of x is 1 plus cosine 2x over 2. In other words, I have to double this angle. So what is double 3 theta? 6 theta. So cosine squared of 3 theta is 1 plus cosine of 6 theta divided by 2. Okay, and take your 2 with the 16, that'll give me 8, right? So that 2 is finished with. Okay, integral of 1 d theta is theta. And again, chain rule. Integral of cosine 6 theta is sine of 6 theta times 1/6. Again, if you differentiate, you would multiply by 6. Since you're integrating, multiply by 1/6. All right, plug in pi over 6. Pi over 6 plus sine of 6 times pi over 6 is pi. Sine of pi is 0. Minus plug in 0, that's 0, that's 0, 0, 0. Okay, in case you're wondering, this happens a lot. Okay, many, many times when you do this cosine squared or sine squared, when you get to this stage, right? A lot of times, the only thing I really get is of substance is this thing when you plug in the theta. Okay, all the rest end up being 0. Now, I don't want you to generalize that that's going to happen all the time. I'll just say it happens a lot. Okay, so these are 0. So 8 pi over 6, 4 pi over 3. Okay. All right, the next one I want to show you is, let's see, 21. Well, I wasn't going to show you the whole thing, but just some of it. whoops, r equals 1 plus 2 sine of theta inner loop. Okay. Now remember the other day we had something like that where there was an inner loop and an outer loop, right? And so we just want the inner loop. So what we had to do is find out where it came into the pole, right? And just analyze from there. Okay, so here's the way I'm going to work that one out. My pen here. R equals 1 plus 2 sine theta inner loop. Okay, now we had something like that last time. I'm not going to bother drawing the whole graph because we don't need it. I just want to know when does this come into the pole. So I solve sine of theta equals negative a half. Okay, so set r equal to 0. Subtract 1 divided by 2. Sine of theta equals negative a half. Okay, so on my unit circle, here's my unit circle. I want the y coordinate to be negative a half. That's here and here. Okay, so what are these angles? That's 30 degrees and that's 30 degrees. So if I go all the way here, that's pi or 6 pi over 6. Add pi over 6, and it's 7 pi over 6. And this is 30 degrees, so I go 12 pi over 6, 2 pi. I back up pi over 6, so 11 pi over 6. Okay. And you might recall from that previous one we did last time, Tuesday, the inner loop was between these numbers, 7 pi over 6 and 11 pi over 6. That bigger outer loop was everything else, right? So it came like this, and then it swung around, then you had an inner loop, right? Then you come back out, and then you get the outer loop. Okay, so you're going to integrate from 7 pi over 6 to 11 pi over 6 of the function. 1/2 times 1 plus 2 sine theta squared d theta. Okay, so I'm going to say et cetera after I square this. Half comes outside. 1 plus 4 sine theta plus 4 sine squared of theta. Okay, and I'll just say et cetera. You finish the rest of that. That's the setup. Okay, that's easy to integrate. That's easy to integrate. This one, use your identity, right? Sine squared of theta. Okay, if you write cosine squared theta is 1 minus cosine 2 theta over 2. So you can use that over there. Okay. All right, so I wanted to show you that one there too. All right, so you take it from there. And the next thing I wanted to show you was a setup for 30. Yeah. 1 plus cosine theta, 1 minus cosine theta. Find the area of the region that lies inside both curves. So how do you do that? Inside both curves. So I needed to graph that. So on the same graph paper, here's the answer, it turns out. I analyze r equals 1 plus cosine theta and r equals 1 minus cosine theta. Okay. So how do I do that? So for both of them, the maximum r is 2. So we played that game before. 10 circle, right? R equals 1/5 circle. R equals 0.2 is 1 circle. Okay, so 1, 2, 3, 4, 5, 1. 1, 2, 3, 4, 5, 2, and waste the 11th, 12th, 13th, and 14th circle. So I made my chart like this. There's no double angle or triple angle, anything, so I just go every 45 degrees. And since I had to do both of them anyway, I put them on the same graph. So here's, I put theta here this time, and R1 and R2. Okay, so this is backwards from what we normally do. We normally put R and theta, but I'm doing this backwards so I can put 1 plus cosine theta, 1 minus cosine theta. Okay. Let's do 1 plus cosine theta. Okay, plug in 0. Cosine of 0 is 1. 1 plus 1 is 2. And likewise for 2 pi, 2. Cut that in half, plug in pi. Cosine of pi is -1. 1 minus 1 is 0. Cut those in half. Pi over 2, 3 pi over 2. Cosine of pi over 2 is 0. 0 plus 1 is 1. Cosine of 3 pi over 2 is also 0. 1 plus 0 is 1. And then pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, all have something to do with radical 2 over 2, which is 0.7. So it's either going to be plus 0.7 or minus 0.7. 1 plus 0.7 is 1.7. 1 minus 0.7 is 0.3. Okay, yeah, you already see the answers. But if your table is like this, I say to myself, I'm going from 2 to 1. So what's reasonable? 1.7. I'm going from 1 to 0, 0.3. 0 back up to 1, 0.3. 1 to 2, 1.7. Okay, then R2, 1 minus cosine theta. Okay, plug in 0. 1 minus cosine of 0 is 1. 1 minus 1 is 0. Automatically, that's 0. Keep cutting in half. That's what I generally do. Pi. Cosine of pi is -1. 1 minus at -1, 2. Cut that in half. Pi over 2, 3 pi over 2. Cosine of pi over 2, 0. 1 minus 0 is 1. Cosine of 3 pi over 2, same thing, 0. 1 minus 0 is 1. And then same thing, here, 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 and here. It's either going to be plus or minus radical 2 over 2, plus or minus 0.7, which means, again, either 1.7 or 0.3. So pretend you don't see these numbers already. So choose either 0.3 or 1.7. You go from 0 to 1, 0.3. You go from 1 to 2, 1.7. Go from 2 back to 1, 1.7. 1 to 0, 0.3. Okay. So I'm ready to plot it. Okay, the green one is supposed to be 1 minus cosine theta. The red one is 1 plus cosine theta. Try to show those. So 1 plus cosine theta. Theta is 0, r is 2. There. Pi over 4, 1.7. Pi over 4, 1, 2. Each one of these is 0.2. So 1.2467. Pi over 2, r is 1. 90 degrees, 1. 3 pi over 4, 0.3. Not very far at all. So I'll aim this way. 0.3 is 1.5 circles. And then pi, I come into the pole. 5 pi over 4, 0.3. So that's over here, but I only go out 0.3. Each circle is 0.2, so I go out 1.5. 3 pi over 2, 1. Right there. 7 pi over 4, 0.3. You aim this way. 0.2, 0.3. And I come back into the pole. Okay, so 1 plus cosine theta looks like this. It's a cardioid. And 1 minus cosine theta turns out to just be the reflection across the y-axis, like so, in green. But I'll show you, just verify that. Okay, 0, 0, pole. 45 degrees, 0.3. I'm looking at the green now. 90 degrees, 1. 3 pi over 4, 1.7. 1, 2, so there's 1.7. At pi, 2. 1, 2 in green. 5 pi over 4, 1.7. aim this way. 1, that's 2, so I back up to roughly there. 3 pi over 2, 1. 7 pi over 4, 0.3. Only a little bit. And I come back into the pole. Okay. So green, 1 minus cosine theta. Red, 1 plus cosine theta. They're both cardioids. Now, for the directions, it says area that lies inside both curves. Inside both curves is all of this stuff, right? I have this, I have this. Now, I didn't draw it perfectly well, as you can tell, but there's symmetry. That matches that, that matches that. In fact, you have an equal amount of area in each quadrant, right? That should match that, should match that, should match that. That being the case, why don't I just take a nice region and multiply by 4, right? Which is the easiest? Quadrant 1. Okay, so I'll just take this piece. Okay, so quadrant 1, I'm going to integrate from 0 to pi over 2, but it's going to be the green graph. So the green graph is 1 minus cosine theta. Okay, so the setup for the area is 4 integral, just in the first quadrant, 0 to pi over 2, 1/2 r squared d theta. Okay, and what is the r I'm using? In the first quadrant, the green, 1 minus cosine theta. Okay, and I'll just say et cetera after that. Okay, take out the half with the 4, 2, square that, blah, blah, blah. So this one was tricky. We had to find out the graphs in order to figure out, okay, there's the common area. It says lies inside both curves. So that's that and that. And I said, oh, by symmetry, why don't I just take the first quadrant part and multiply by 4 because I like the first quadrant. I'm going to be using 0 and pi over 2. Okay. All right, so that's the way that one goes. Okay, there's another one, 31 star. I'll do that a little bit later, but I want to show you this one. And now I'm going to go back. I know I'm going a little bit out of order here. Okay, what is this? Inside the first curve, outside the second curve. Inside the first, outside the second. How do I do that? So 23, r equals 2 cosine theta, and r equals 1. And that's not the same as your question, but again, it's the same concept, same idea. Okay. Book has 4 sine theta and r equals 2, but same concept. Okay, I don't need an entire graph here. I just need to figure out where I am. Okay, so I need to know where they touch, so I set them equal. 2 cosine theta equals 1. Cosine theta is 1/2. Okay. X coordinate is 1/2. So I draw my unit circle. R is going to be 1 anyway. And that looks like pi over 3 and negative pi over 3. Okay, now R equals 1 is a circle of radius 1, right? So there it is. They touch here and touch here. So let me just pick a number other than negative pi over 3 and pi over 3 that this graph goes through. So it looks like I have to go from negative pi over 3 to pi over 3. What's a nice number between them? 0. Okay, so if I plug in 0, cosine of 0 is 1. times 2 is 2. Okay, so whatever this thing looks like, it goes further out. So this is the region that I want. Okay, so again, by the directions, it is inside the first curve, but outside the second. So it does not include any of r equals 1. So this is the region in question. Okay, so this is kind of like upper minus lower, which was the first kind of problems we did in our course, way back on day 1 or 2 or so, right? So, so watch what I'm doing now. If I integrate this function from negative pi over 3 to pi over 3, I'm tracing out this. So watch what I'm doing. From negative pi over 3 to pi over 3. Okay, do it again. You have that, all of that, and back. Okay. If I do the same thing with r equals 1 from negative pi over 3 to pi over 3, I'm tracing this, that, and that. Essentially, that's the area that I'm throwing out. It's like upper minus lower. Okay, so it's almost like at the beginning of our course, right? When we had something like this. F of x, g of x. And we're integrating from a to b, right? Okay. Well, if I take this area down there, that's the integral of f of x. If I take this area, that's the integral of g of x. So if I only want this, it's upper minus lower, right? The integral of f of x minus g of x in rectangular coordinates. Okay, so in polar coordinates, it's the same concept. Okay, I'm taking the upper function, the outer one, which is sweeping all of that. So if I didn't have that, if I didn't have, here we are. If I didn't have r equals 1, the area would be traced out by all of this, but I'm throwing this piece out again. So I'm tracing that one I'm throwing out is the integral of the inner radius, which is 1. So here we go. And you can tell I have symmetry. So by symmetry, I'm not going to integrate from negative pi over 3 to pi over 3. I'll integrate from 0 to pi over 3 and double it. So 2, that's a 2 there, integral from 0 to pi over 3 of upper minus lower. So the upper function, the further out, is 2 cosine theta. So 1/2 big R squared, 2 cosine theta squared, minus 1/2 smaller radius squared, which is 1 squared. Okay, so that's what happens. Now, what did I do over here? 2 squared is 4, times 1/2 is 2. So 2 cosine squared. And this is just minus 1/2. Okay, I'm deciding to distribute the 2 back in. Put the 2 back in. 4 cosine squared theta minus 1 d theta. Okay, so this is 4 times formula for cosine squared. 1 plus cosine 2 theta over 2 minus 1. 4 divided by 2 is 2, right? So it's going to be 2 times all of this. So 2 times 1 is 2. Whoops, what did I do here? 1 plus cosine 2 theta over 2. Right, so that's a 2. And I think I messed up. This should be a 2 here. Right, that should be a 2. So I goofed. That's a 2. Right, so that means this should be a 2 theta, my bad. 2 theta. So I'll correct it on the fly. And this is 2 cosine 2 theta. Integral is sine of 2 theta times 1/2. That works out perfectly. So I messed up over here. That should be 2 theta. Okay. Double check. The derivative of sine 2 theta is cosine 2 theta times 2. Okay. So if I plug in pi over 3, this should be a 2 pi over 3. Plus sine of 2 pi over 3 minus nothing plus nothing. That's still nothing there. Sine of 2 pi over 3. 2 pi over 3 is over here. The y coordinate is radical 3 over 2. Okay, it wasn't that bad. I just have to change this to 4 now. So I think that's okay now. Multiply by 2, multiply by 3. Yeah. So final answer, 4 pi plus 3 radical 3 all over 6. Okay. Okay, then 27, I believe 27 matches. 3 cosine theta, 1 plus cosine theta. Yeah, that's what I got also. Okay, so again, for this one, I'm not going to waste a polar graphic on that. I just need to find out where they touch and then figure out which is the upper and which is the lower, so-called. Okay, so set them equal. 3 cosine theta equals 1 plus cosine theta. Subtract cosine theta. 2 cosine theta equals 1. Divide by 2. Cosine of theta is a half. X coordinate is a half. Okay, that's at 60 degrees and negative 60 degrees. So negative pi over 3, pi over 3. Okay, which is the upper, which is the lower, so-called. So pick something in between, like 0. Put a 0 here. 3 cosine of 0, 3 times 1 is 3. So that goes out to 3. Plug in 0 here. Cosine of 0 is 1. 1 plus 1 is 2. Okay, so that clinches 1 plus cosine theta is the lower function. 3 cosine theta is the upper function. It's upper minus lower, just like this one, upper minus lower. And again, I'll take advantage of symmetry. So instead of going from negative pi over 3 to pi over 3, 0 to pi over 3 multiplied by 2. So integral from 0 to pi over 3, 1/2 big R squared, 3 cosine theta squared, minus 1/2 little r squared, 1 plus cosine theta squared. And very conveniently, the 2 cancels these halves. Factor out a half, it'll cancel the 2. Okay, 9 cosine squared theta. That's gone. Okay. If I square this, it's all positive, right? A squared plus 2ab plus b squared. So I have 3 positive terms. This negative means I'm going to have 3 negative terms. So it's going to be minus, minus, minus. So I'll square this, except they're all going to be negative signs. Minus 1, minus 2 cosine theta, minus cosine squared theta. Okay, and these two give me 8 cosine squared theta, minus 2 cosine theta, minus 1. That's easy, that's easy. There's cosine squared again. It's our old friend. 8 times 1 plus cosine 2 theta over 2. That cancels out. 8 with 2 giving me a 4. So let's see if I don't mess up this time. 4 times 1 is 4, minus that 1 is 3. Plus 4 cosine 2 theta, minus 2 cosine theta. Okay. So I think we're good. So integrate. Integral of 3 theta. Integral of 4 cosine 2 theta is 4 sine of 2 theta times a half. 4 times a half is 2. Integral of negative 2 cosine theta is negative 2 sine theta. Remember, you can always double check your integration by differentiation. What's the derivative of this stuff? Derivative of 3 theta is 3. Derivative of 2 sine 2 theta is 2 cosine 2 theta times 2, so you get to 4. And derivative of negative 2 sine theta is negative 2 cosine theta, so that works. Okay, so from 0 to pi over 3, when you plug in 0, you do get 0. 0, sine of 0 is 0, 0, so these are all zeros. Plug in pi over 3. 3 times pi over 3 is pi. 2 sine of 2 pi over 3 minus 2 sine of pi over 3. Sine of 2 pi over 3 and the sine of pi over 3 are equal. That means they cancel out. Okay, if you look at pi over 3, 2 pi over 3, they have the same height, radical 3 over 2. So my final answer is just pi. All right, now getting back to 30, okay, the one that I just did, because I want to go back to these, but spent a lot of time with this. Now I'll go back to integrate this. All right, so I had said we're doing 4 times the integral from 0 to pi over 2 of 1/2 this radius squared, 1 minus cosine theta squared d theta, etc. So yeah, I just realized I finished the etc. here, so might as well clean that up for you. So 4 times 1/2 1 minus cosine theta squared d theta. Okay, I'll finish that. 4 times 1/2 is 2. 1 minus 2 cosine theta plus cosine squared theta. There's cosine squared again. 1 plus cosine 2 theta over 2. 1 minus 2 cosine theta. That stays the same. Have this now. Okay. And at this stage, I don't like that fraction, so I'm going to put the 2 back in. 2 times that, 2 times that, and 2 times that will just cancel the 2 in the bottom, right? So at least I have no more fraction. So 2 times 1, 2 times that, and 2 times that fraction will just drop the 2's. Come over here. So now it looks like that. 2 plus 1 is 3. 3 minus 4 cosine theta plus cosine 2 theta. Okay. So we integrate. 3 theta. Integral of negative 4 cosine theta is negative 4 sine theta. Integral of cosine 2 theta, sine of 2 theta times 1/2. Okay, plug in 0, you get 0. 3 times 0 is 0. Sine of 0 is 0, so that's all nothing. Pi over 2. 3 times pi over 2, 3 pi over 2. Plug in pi over 2. Sine of pi over 2 is 1. 1 times that is negative 4. Plug in 0, you get 0. So 3 pi over 2 minus 4. I'll write it as 3 pi minus 8 over 2, like this. Okay, I'll show you one more before it's just about break time. I'm calling it 31 star. So we're not going to do the original problem with double angles. Sine 2 theta, cosine 2 theta. I'm just going to make them thetas. Okay, so sine theta, cosine theta. And let me see if I can find that one for you. Whoops. My paper flew away here a second ago. Right after it. $31 star. So don't look in the back of the book. It's going to be a different number. R equals sine theta, R equals cosine theta is what I'm going to do instead. Okay, now for the directions, we're still going to keep it. Find the area of the region that lies inside both curves. So inside both. So sine theta, cosine theta. There's a reason why I changed it also. It makes the problem much easier, but I'm piggybacking off of this for the next section that we have to deal with. Okay, so I didn't bother to use a polar graph paper here. I knew the maximum R for both of them is 1, right? So I just draw my own thing. Okay, and sine of theta, cosine theta is pretty straightforward. Sine of 0 is 0. Sine of pi over 4 is radical 2 over 2, 0.7. 1, radical 2 over 2, 0. Then it goes negative. Negative radical 2 over 2, negative 1, negative radical 2 over 2, 0. Okay, so sine in red starts at the origin. Pi over 4, 0.7. Pi over 2, 1. 3 pi over 4, 0.7. Pi is 0. Where's the rest of the graph? It must retrace its steps again, and it does. So we'll see 5 pi over 4, you're aiming here, right? But negative 0.7, we already got that. 3 pi over 2, negative 1. You aim this way, but you back up. We already got that. 7 pi over 4, you're aiming this way. Negative 0.7, back here, already got that. And then 2 pi, you're back to 0. So there we go. And cosine is going to be over here. Okay, cosine of 0 is 1. Pi over 4, radical 2 over 2, 0.7. Pi over 2, 0 comes into the pole. 3 pi over 4, you aim this way, but it's negative 0.7, so it ends up coming here. Pi means you aim this way, but it's negative 1, so you back up. And again, it just retraces its steps. 5 pi over 4, negative 0.7, that's back here. 3 pi over 2, 0, come back to the pole. 7 pi over 4, 0.7, and 2 pi back to 1. Okay, so here's r equals sine theta, r equals cosine theta. Area between the two curves is right here. Okay, so where do they touch? They touch at pi over 4 and the origin or the pole. Okay, I'll use symmetry. Okay. By symmetry, you get as much area here as here. So I'll only go from 0 to pi over 4 and double it. Okay. But if I do that, which function am I integrating over? The cosine or the sine? Okay. It's the sine function. It's the red function that's between 0 and 45 degrees, right? Not the green one. The green one starts at 45, it seems, and comes to 90 degrees. Okay. So the area is 2 integral from 0 to pi over 4 of 1/2 r squared d theta. Okay. So 0 to 45 degrees, 2 and 1/2 cancels out. Sine squared of theta, 1 minus cosine 2 theta over 2. Okay, factor out the half. Integral of 1 is theta. Integral of cosine 2 theta is sine of 2 theta times a half. 0 to pi over 4. Plug in 0, you get 0. Plug in pi over 4, there's a half in front. So pi over 4 minus 1/2. Okay, if I plug in pi over 4, I'm taking the sine of pi over 2, which is 1. So it's negative a half times 1. Okay, so trying to clean this up, 1/2 of pi over 4 minus 2 over 4, which I'm going to write as pi minus 2 divided by 4. Half of that is pi minus 2 over 8. So the answer is pi minus 2 over 8. Okay, the problem's finished. What I'll do starting after the break is we kind of assumed the points of intersection were 0 and pi over 4. Let's see if we actually come up with that. Okay, you'll see something unusual happening, and that'll help us for the rest of the problems in this section. Okay, so I'm going to work on the points of intersection of this graph, sine of theta, cosine theta. So where do they touch? Now you can just look at the picture. They touch at 0 and pi over 4. Okay, but what happens when we actually try to solve this? Okay, and we'll do that after we break. Okay, so let me stop the share right now. I think some of you put something in the chat. So let me see. Yeah, some of you came in a little bit late there. So yeah, if you came in late, please send me an email again. I may not remember that. Okay. What does the area of a spiral look like visually? Okay. If I can just show you quickly here. Okay, so we had a spiral shape, something like this, right? So if you're going from 0 to 2 pi, then you'd be sweeping around this area. And you can see it's a real weird shape, right? How do you do that in X and Y? I wouldn't know. But in polar coordinates, you can figure it out, right? So you're sweeping around this area like so, if you're trying to find the area of a spiral. Okay, so let's break. I see it's 8:08 roughly. So 820. Okay, start up again at 820 or so. Okay, all right. Okay, folks, let's continue on. So, okay, how do you enter sine squared of x on a calculator? Assuming your calculator accepts something like that, you would normally go sine of x parentheses squared. Some calculators can't do that, but if your calculator allows functions, you would write it like so, sine of x squared. Or if you have the option of raising it up, sine x squared like that. Okay, but normally on a calculator, you don't type it like so. We're talking about how to get that on the calculator. Okay. All right, so I'm almost done with 10.4. So I've shown you all the stuff about area. There are some questions about points of intersection. So it won't take me that long to do that. I'll do a little bit of 10.5 and then I'll stop and give you the quiz. Okay? So about finding points of intersection. So let me go back to finding points of intersection of sine theta and cosine theta, the 31 star. And again, the reason why I want to do that is to show you, this particular example. Now we know just by looking at it, they touch at 0 and pi over 4. But how do we normally find points of intersection? Okay, when we were doing stuff with x and y, like the beginning of our course, we had two graphs. How do you know where they touch? Set them equal to each other, right? So suppose you had, I don't know, y equals 4x minus 3 and y equals x squared minus 5x plus 6. Where do they touch? You set them equal. Right? Don't write any of that down. That's just a concept. So set these equal. Sine theta equals cosine theta, or divide both sides by cosine theta. Tangent theta equals 1. Again, we know by looking at it that they touch here and here, 0 and pi over 4. But let's see what happens when I set them equal. Tangent of what angles comes out to be 1? Well, pi over 4, 5 pi over 4. Because at pi over 4, both x and y are radical 2 over 2. So if we divide sine over cosine, you get 1. 5 pi over 4, they would both be negative radical 2 over 2. So if you divide, you also get 1. So as a point, r comma theta, the angle is pi over 4, and the r is radical 2 over 2. Remember, we're always supposed to write it as r theta, not theta r. Negative radical 2 over 2, 5 pi over 4. But I'm crossing this out. Again, look at these two. Look carefully, they are the same point. They are pi radians across from each other, 180 degrees, and one is the opposite of the other. Okay, or think again of at pi over 4, radical 2 over 2, 0.7. 5 pi over 4, you aim this way, but you back up 0.7, you're at the same point. Where's the pole? We never got the pole. The reason is because what are the coordinates of the pole? Talked about this before. It's 0 comma theta. Okay. Any angle will do. Okay. So in polar coordinates, say what's the pole? We say the origin in x and y. In polar coordinates, we're supposed to say the pole. You could say 0, 0, but this is 0 pi over 4. This is 0 pi over 2. 0, 3 pi over 4. I mean, think of just changing the angle, right? Okay, 0 is aiming that way. Pi over 4, you aim that way. Pi over 2, you aim that way. 3 pi over 4, you aim that way. But how far do you walk out? 0. So if you walk out 0, it doesn't matter, right? You're changing your angle, but you're not walking anywhere. So the pole is 0 comma theta. Any theta will do. What happens in the graphs is you can see from the graph, they both come into the pole, but not at the same theta. Okay, in fact, you can tell right over here. Here we have 0 and 2 pi, but where's 0 here? Pi over 2 and 3 pi over 4, 3 pi over 2. Now, we never had that issue in x and y, you might recall. Right? X and y, there's only one way to label a point. So if I have an xy coordinate system, right? Pretend this is x and y, I put a dot over here. There's only one way you can label it, right? How far can you go in x? How far do you go in y? But because of the idiosyncrasies of polar coordinates, right? You have the possibility of having more than one way of labeling a point. Okay. In case you're wondering what this was, this indicates that the sine was that one, the cosine was that one. So that's why I integrated with the sine function, because the sine function was from 0 to 45 degrees. Okay. In a nutshell, what are the coordinates of the pole? 0, comma, anything. All right. All of that now to piggyback off of how to do these problems at the end now. Find all points of intersection. Okay, and again, your problems may not match mine. In fact, I'm noticing 37 doesn't, and 41 does. But anyway, be that as it may. So please make a note of this. Intersection problems in polar coordinates. Okay, in rectangular coordinates, right? You have two graphs. I don't know, y equals 3 sine theta and y equals 1 plus sine theta. Set them equal to each other. In polar coordinates, you have to do the following. Set the equations equal. That's just the normal technique. And check the pole, which really means, can r equal 0 for both equations? Is there any possibility for r equaling 0? If the answer is yes, they intersect at the pole. So getting back to this picture, what are the points of intersection? Radical 2 over 2, pi over 4. We got that by setting them equal to each other. But they also touch at the pole. At different angles, though. So by setting the two equations equal, we weren't able to get it. Right? In x and y, that issue never comes up again. Right? You say, okay, they touch at 3 comma negative 10. That's set in x and y, but not in polar coordinates. Okay? When you look at this graph, hey, they seem to touch at the pole. They do touch at the pole, but at different angles. Right? For sine of theta, it comes in at pi and 2 pi. Cosine comes in at pi over 2, 3 pi over 2. So this technique of setting the two equations equal misses that. So you always must check the pole for those kind of problems. Okay, so here we go. 37, my 37, which I'm noticing is not your 37, but anyway, same idea. Find points of intersection. 1 plus sine theta, 3 sine theta. Okay, so first I'm going to say, can this ever touch the pole? Is it ever possible for r to be 0? The answer is yes. Can this thing ever be 0? Well, this thing here has to be negative 1, right? Can the sine of theta ever be negative 1? Sure. South pole, 270 degrees, so that's a yes. Can this ever be 0? Yes. Let sine of theta be 0, which is at an angle of 0. Okay, so automatically they touch at the pole. Okay, so one more time. How do you check the pole? Ask, can r equal 0 for both equations? Can this ever be 0? Yes. Can this ever be 0? Yes. Therefore, they touch at the pole. Now I set them equal to each other. 1 plus sine theta equals 3 sine theta. Subtract sine theta. 1 equals 2 sine theta. Sine of theta is a half. I.e. y coordinate is a half on a unit circle. I go half a unit up. There are my angles, pi over 6, 5 pi over 6. Okay, plug in pi over 6. Sine of pi over 6 is a half. Plus 1 is 3 halves. Same thing over here. Sine of pi over 6 is a half. Half times 3 is 3 halves. 5 pi over 6 gives me the same thing. Plug in 5 pi over 6. Sine of 5 pi over 6 is a half. Half plus 1 is 1.5. Or if you plug in here, same thing. Sine of 5 pi over 6 is a half. Half times 3 is 3 halves. Okay, and do we throw either of these out? Okay, remember before, we said if 2 points represent the same, two ordered pairs represent the same point, then you throw out one of them, preferably keep a positive sign. These are different points. All right, so how do I present my final answer? 3/2 pi over 6, 3/2 5 pi over 6, and the pole. Notice by setting these equal to each other, I missed the pole. Okay? They both touch the pole, but not at the same angle. Okay? This one gets 0 when theta is what? 3 pi over 2. But if I plug in 3 pi over 2 here, I don't get 0. Okay? They touch at the pole because r can equal 0 here, r can equal 0 here. Okay, so that's the idea behind this one. Okay, 41, which does match your 41, and then I'm done. Okay, so before I go to that, I think I've done everything I wanted to do from 10.4. Okay, so I'll make some introductory remarks about 10.5, and then I'll give you guys the quiz. Okay, so I'm finished with 10.4. I was supposed to finish 10.3, so I'm one section ahead. Okay, and we're still aiming for what? November the 10th for the next exam. Even if I finish early, I'll just go on ahead. And I think I need to get ahead because I don't think you want to have the last test on December 15th. I'd rather push it up if possible. Right? And yeah, we have a holiday for Thanksgiving on November 26th also. Okay. R equals sine theta, R equals sine 2 theta. By the way, I just mentioned off to the side, I'm not doing 39, but I'll just mention 39. R equals blah, 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 R equals 1. Okay, this one never comes into the pole, obviously, right? Can R ever equal 0? No, because R equals 1, which is your basic unit circle. Okay, so this one, you don't have to worry about it. So find points of intersection, you would just set them equal and go from there. Okay. All right, can this come into the pole? Yes. Can this come into the pole? Yes, at 0. So I definitely have the pole. So what's the pole? R equals 0. Why don't you say 0, 0? 0, 0 works, but it's 0, comma anything, right? The pole is 0, comma any angle you feel like. It can be 316 degrees or negative 521 degrees. They all work. Okay, to set them equal now, I'll use the identity. Sine of 2 theta is 2 sine theta cosine theta. Set them equal. Okay, move the sine theta over. 0 equals 2 sine theta cosine theta minus sine theta. Factor out the sine of theta. Sine of theta, parentheses, 2 cosine theta minus 1. So by the 0 factor property, either this is 0 or this is 0. Sine of theta is 0. 2 cosine theta minus 1 equals 0. That gives me cosine of theta is 1/2. Okay, sine of theta equals 0. That happens at 0 and pi and 2 pi, but we don't get anything else. Okay, so if I plug in 0, I get r equals 0. That's the pole. I already got it. And if I plug in pi, sine of pi is also 0. Okay, so I have 0, 0, 0, pi. Those are both the pole. I already got the pole, so it's redundant. But that's okay. It doesn't matter. So I'm crossing them both off because I already got the pole. Okay, cosine of theta is 1/2. X coordinate is 1/2. That's here and here. So pi over 3, 5 pi over 3. Okay, so I plug in pi over 3. Sine of pi over 3, sine of 60 degrees is radical 3 over 2. Plug in 5 pi over 3. You can plug in either this one or this one. This one's easier. 5 pi over 3 is over here. The sine is negative radical 3 over 2. Okay, so I have the pole, radical 3 over 2, pi over 3, negative radical 3 over 2, 5 pi over 3. Okay. Now, if you look in the back of the book, it shows the pole, it shows this one, but it doesn't show this, it shows this. Can you see why? Take a look at this and this. Negative radical 3 over 2, 5 pi over 3. positive radical 3 over 2, 2 pi over 3. They are the same point. These are 180 degrees off from each other. Here's 5 pi over 3. Here's 2 pi over 3. Okay. The back of the book says, okay, if we have to present our answer, let's not give our answer with a negative r. Let's write it with a positive r. So radical 3 over 2, 2 pi over 3. So that's the way it's written like so. Okay. All right, so that's it, folks. So I'm done with 10.4. I'll just show you where we're headed for 10.5. I won't get that far, and then I'll stop and give you the quiz. All right. So 10.5 is on the conic sections, so-called. So we're studying the ellipse, the parabola, and the hyperbola. So why is it called conic sections? By the way, there's also a circle, but we've analyzed a circle many times before. Right? So if you take this cone, and this is a true mathematical cone, there's a branch that goes up and also down, and it goes on forever, infinitely. Okay. Now, I know you're probably used to a cone, like an ice cream cone. It stops. It doesn't have this bottom thing, and we just go like that. There's nothing wrong with that. That is a good definition of cone. But some applications of a cone, you want the whole thing, which means this goes up infinitely high, and you have this branch here goes infinitely low. Okay, so they're called conic sections because if you cut a certain way, if you cut like this, you see the ellipse. Okay, now if this was straight, cut across here, you could see a circle, right? We already seen the circle. If you make a cut like this, which is parallel to this line, you would have your parabola. And if you cut like so, you have a hyperbola, which has a branch like that and a branch like that. These two branches together are called a hyperbola. Okay, so we're going to study the parabola a little bit more. You said we've done a lot of parabolas, yeah, but we're going a little bit more in depth. So here's a parabola. Okay. There are going to be 4 basic parabolas, as you can probably guess, opening up and down, which you're probably already familiar with, but right and left. Okay, so these are 4 basic parabolas. Okay. A parabola can be determined by 2 points called the focus and directrix. Okay. The directrix is a line. Focus is a point, as you can see here. So how can one point and a line give me a parabola like this? Okay, so what they're trying to show you in this book, and this is on my page 674. Okay, this is a point in a parabola if the distance away from the focus and the directrix is the same. So take a look at the distance from this point to the vertex, and from the vertex to the directrix, it's the same. Okay, and you've probably seen this mark before in your high school geometry, maybe. That 1 mark, 1 mark, 2 marks, 2 marks. That means this is the same as that, that's the same as that. So this is a point on a parabola because this distance away from the focus and this vertical distance to the directrix is the same. And if you have a point way out over here, this distance, again, distance from the focus, distance to the directrix is the same. So if you take all the points that are the same distance away from the focus and the directrix, you end up with a parabola. Okay. Now, you can go through all the mathematics of that. So they worked that all out. Okay, you can look at it if you want to, but you don't really have to. Okay, I'll just give you the final result. X squared equals 4py. Okay, p is called the focal distance, or focal length, focal distance. X squared equals 4py is an equation of a parabola which opens up and down. As you might guess, if p is equal to 1/4, 4 times 1/4, then you have your famous x squared equals y, or y equals x squared. So like that, or like that. Okay, that's x squared equals 4py. As you might guess, if it's going right and left, it's reversed. Y squared equals 4px. Just gets reversed. So y squared equals 4px, like that. Okay, and depending on the sign, you know how the sign determines it, right? Okay, so if we have a positive, it's up. negative is down, positive this way is right, negative is left. Okay, that's y squared equals 4px. I'll show you more next time. Then the ellipse. Ellipses look like this. Or they can look like this, right? Bulging in one direction, like that. How do you get an ellipse? Okay, you have two foci, one focus, two foci, okay, and you have a distance, okay, certain distance. Okay. The points on the ellipse have the category or property that the distance away from F1 plus the distance from F2 is always a constant. Okay, they write that here. The absolute value means the distance from P to F1 plus the distance from P to F2 is the same number. They call it 2a. Okay, if you can imagine, you have point here, imagine you have a string, right? You have a string that's longer than the distance from F1 to F2, and you hold it taut, so you just hold it. So the string distance is the same, right? And imagine just swinging that string around like that, and do the same thing here. You end up with an ellipse. Okay, and the bulge might go this way also. So here are the two foci going like that. Right, so you end up with equations of the ellipse. Okay, and they give you the equations here. I'm just going to say it quickly. We'll do more of it next time. And by the way, you can put all these on your cheat sheet if you want. Okay, so x squared over a squared plus y squared over b squared equals 1. How do you get that? If you do the heavy-duty mathematical calculations here and actually found the distance, they worked it all out, okay, and do all this heavy-duty algebra, this is what it ends up being. Okay. And then the hyperbola looks like this. Okay, there are two branches. For the hyperbola, you also have two foci. Instead of having the sum being a constant, you have the difference being a constant. Okay, so this distance minus this distance is a constant. Okay. It could be plus or minus, so they say plus or minus 2a. Okay. Or the distance from this point to that focus minus the distance from that point to that focus is the same number, 2a. Okay. And all the heavy-duty calculants end up being the same. Only difference, as you might guess, is that for the hyperbola, instead of a plus, it's a minus. Otherwise, the equations look almost the same. There's a minus. Okay. So what are we getting? We got the parabola. So what do you want for the parabola? X squared equals 4py. That's going to open either up or down. Y squared equals 4px, left and right. You will notice in all of these cases, the focus is on the inside and the directrix is on the outside. Okay, so opening up, focus, directrix. Opening down, focus is on the inside, directrix outside. Opening right, focus, directrix. Opening left, focus, directrix. Okay. I'm just mentioning something quickly about the word focus, more from a physics standpoint. So I'm not testing you on this, but maybe your physics teacher is going to have you, use this about the concept of focus, the English word focus, right? Turns out if you take parallel rays or parallel lines, if you draw a whole bunch of vertical lines coming straight down and they bounce off the parabola, and the property in physics that the angle of incidence is equal to the angle of reflection. So if you bounce these off, they all go through the focus. So if you bounce off here, it comes through here. If you go down here, obviously if you come straight down here, it bounces back to there. If you come straight down there, it bounces to the focus, which is the reason why it's called the focus. So it'll all focus over here. And it goes in reverse also. So let's say you have a light source emanating from the focus. Okay, the light will bounce here and here and here, and they'll all end up bouncing in a straight array like so. It's my understanding that your headlights, the headlights on your car are parabolic. Okay, so you have your light source for your headlights, right? It'll bounce off the parabolic reflector and then go straight, so you can see where you're going. I mean, you don't want the light going that way and all over. You want them all to go straight out to wherever you're aiming for. So hence the word focus. So you can show mathematically and from physics that if you bounce off a parabola, it'll go through here. And that same principle for parabolic dishes, right? Although that's a three-dimensional object, and you'll learn about that three-dimensional objects more in Calc 3. But the three-dimensional object of a parabola, it's called a paraboloid, actually. But you've seen those parabolic dishes, right? There's that focus that's there, right? So if you bounce rays, parallel rays off that parabolic dish, right, then it all bounce over to the focus. And it goes backwards. If you emanate something from the focus, right, you take the source coming from the focus and let it go, and it bounces off the parabolic dish, then it'll all go out in the same direction. Okay, so that's how that works. Okay, and then just mention something also quickly for physics again, not holding responsible for it, but a property of the ellipse. Okay, can you guess what happens if you bounce something off a focus in an ellipse? It'll always bounce through the other focus. So pretty obvious if you bounce this way. If you bounce here, it bounces straight back. Of course, it goes here. And the halfway one is also obvious. If you kind of go directly there, you can tell by geometry and symmetry it should go here. But what's not so obvious is if you bounce here, it'll also go there. Or if you bounce back there, it'll come over here also. So these two foci are like so. Okay, and they have important properties in physics. Again, it's my understanding there are a lot of good applications for this. I don't know if you've ever been to the Exploratorium. I think it's more parabolic, but elliptical also is possible. You could have someone sitting here and sitting here. If there's an ellipse, you could talk very softly, and the other person would be able to hear if it looks like this. Okay, or if you have a parabolic dish, I think the one in Exploratorium is parabolic. So if you have, a parabola like this and another one similar on this side, you could talk very softly, but because of the focusing effect, that gets magnified, so you can actually hear somebody. They might just talk very softly, maybe many feet away, but you can hear them if it's bounced off of a parabolic dish on each direction. Okay, so I'm not testing on that, but I was supposed to share that with you as what these things are good for, what they're useful for. Okay, so we'll learn more about the parabola, the ellipse, and hyperbola a little bit more next time. Okay, but that's about it for now. So I'll stop. Let me check the chat and see where we're at. Okay, I don't think I see anything else there. Okay, so we're good. Okay, so get ready to have your cell phone, and then I'll make your breakout rooms as usual. And if your breakout room ends up not having enough people as usual, then I'll move you to a different room. And we're still recording, so worst comes to worst, you can always check the recording. Okay, and as usual, due next Tuesday at our starting time. And don't forget, you actually get 1 more hour this weekend, right? So you have 1 more hour to do it because of finishing daylight saving time. So this weekend, you actually get 1 more hour. Okay, so here we go. Okay, very simple. Draw the graph of r equals 3 sine of 2 theta. R equals 3 sine of 2 theta. Show your chart. Spread out your graph according to the principles discussed in class. Okay, so I'll talk a little bit more about that. What is the maximum R in this case? You don't have to blurt it out. It should be pretty obvious. And we did some problems already with that. So you must use your standard polar graph, right? The one that I gave you on mathbits.com, the one that looks like that. It's just every 15 degrees, and there are 14 circles, right? So you must use that one. There was something special about the 2 theta, so that changed the way the chart worked also, right? So use that to figure it out. So what's the maximum R? Spread out your graph appropriately. You'll be graded based on that also. So you might have the right graph, but I'm not going to give you full credit if you scrunch the graph only to a few circles. You want to use as many of the 14 circles as possible. And there's a certain way to handle sine of 2 theta. Okay, so it's R equals 3 sine 2 theta. Draw the chart and draw the graph due Tuesday at 7:10 p.m. Okay, I'm going to assume you all have it now. So get started with it, and let me set up your breakout rooms. and you can leave after that anytime between now and 9:25. Okay, so let me get that ready. Okay, you should have an invitation to join your breakout room. So can everybody please join your breakout room now? Most of the time I'll
Professor Hom, could you put me back in a breakout room? I accidentally left.
Bing, if you can hear me, please join your room. Otherwise, I'll just have you leave.